Hi everyone. Hi everyone. I'm Eleonora. Today I will talk about the hidden millimeter universe, and I will tell you what radio telescope can see that optical telescope miss. This is the overview of my talk. Firstly, we are going to speak about how the universe appears to us in the visible light. Then I will tell you how a telescope works, and then I will show you how actually we observe and study in the millimeter sky. So let's talk about how the universe appears to us. Generally, when we think of light in our everyday life, we think about what we can see with our eyes. But in physics, the term light is refers more broadly to any electromagnetic radiation. So basically, the radiation that travels through space in a form of waves at the speed of light, so of 300,000 kilometers per second. One important property of light is its wavelength, that basically is the distance between two consecutive peaks of the wave, and the energy that is carried by the radiation is strictly correlated to the wavelength. In fact, in this example, the red wave has a large wavelength, and so it will carry less energy, while the blue wave that has a shorter wavelength will carry more energy. If we put together the lights that we can observe at any wavelength, we have the electromagnetic spectrum. That is basically the complete set, the complete range of waves from longer radio waves, etc., to shorter wavelength. The human eyes, that are two very sophisticated instruments, basically can see only a tiny range of the electromagnetic spectrum. This range is what we call the visible spectrum, and it spans between 9.3 and 9.7 micron. It means that this is only a millionth of a meter, or better, a thousandth of a millimeter. So the wavelength is very small. In the electromagnetic spectrum, we have waves that can go that have wavelengths from the size of buildings, so tens of meters, up to wavelength of the size of atoms and atomic nuclei, so very small wavelength. My research is basically focused on observing the microwave, so wave with a wavelength of the order of millimeters, but let's say a little bit on what we can see in the visible spectrum. So as I said to you, the human eye can only see a very small range of wavelength. And fun fact, it's not a coincidence that this range corresponds to the emission peak of the sun. In fact, in this plot, we are basically seeing the amount of radiation that the sun emits as a function of the wavelength. And so this basically tells us that the human eye evolved and is sensible to the radiation that is most emitted by the sun itself. Let's see a little bit what type of object we can see in the sky when we observe the sky with an optical telescope. We can see nebulas that are the results of stars exploding and dying. We can see the rings of relativity that are basically how gravity works in space. We can see the light echoes of a supernova, so basically when the echoes of light that are emitted when when a star explodes. And this example here is a supernova in the Cigar galaxy. We can see a lot of different galaxies with a lot of different shapes. And lastly, we can study and observe planets. All these pictures that I showed you were made with the Hubble Space Telescope. There is a reflective telescope, and later we will discover what this means. This telescope has a mirror of 2.4 meters. It is equipped with 5 main instruments, and it's been working for 35 years. This telescope is actually a satellite, so it's not located on Earth, and it's located at about 1.5 million kilometers from Earth. And basically, if you want to drive with your car to, let's say that you can do it, but if you want to drive with your car to where Hubble is located, if you go at a velocity of, I don't know, 100 kilometers per hour, it will take you 625 days to reach Hubble, so almost 2 years. Okay, but now let's see how a telescope works. And what is the difference with the radio telescope? So the telescope that can observe the radio waves and the microwaves. So to do so, we have to introduce some basic concept of optics. The first one is the angular resolution. So basically, we have to decide when buying or when building a telescope the scale that we want to observe in the sky. So basically, we want to decide the minimum detail that we are able to distinguish in the sky. And so we have to decide the angular resolution. These characteristics of a telescope is strictly related to how to the structure and also the components of which the telescope is composed. Basically, a general rule is that the larger the telescope diameter is, the higher the angular resolution will be. So in this case, here we have a larger telescope than this image take here, where we can't resolve the two point sources. The angular resolution is not only related to the diameter, so the structure of the telescope, but also on the type of radiation that we want to observe. In fact, if we take a telescope with a fixed diameter, in general, if we want to observe, if we are observing a radiation with a smaller wavelength, we will see more details than if using the same telescope, we are going to observe waves with larger wavelength. And this will be important after when we talk about radio telescopes. Okay, the other important concept that we have to introduce is how the functioning of two optical systems, so lenses and mirrors. A lens is basically an optical component that can converge or diverge rays of light by means of refraction. And the refraction is simply the redirection of light when passing through from a medium to another. A simple lens is basically composed by a single piece of a transparent material that it can be glass or plastics, and it can also be arranged in a series of lenses aligned all on the same axis. I told you that a lens can be converging and diverging, but which one of these do we use to build telescopes? We use converging lenses because we want to converge the light that is coming from the sky to a specific point where we will locate our eye a camera or sensor or detectors. Okay, and basically this is also how your glasses works. Then we have to talk about mirrors. A mirror, I think you all know how a mirror works, but basically a mirror takes the light coming from an object. The light is bounced off on the surface of the mirror and is redirect on another spot. Knowing the functioning of these two objects, we can build two different types of telescope. A refractive telescope that is basically a series of lenses, and a reflective telescope that is a series of mirrors. You can see that these two types of telescope are different in structure. For example, the refractive telescope is slimmer and it's longer, while a reflective telescope is thicker but it's shorter. And I told you that the angular resolution depends on the diameter of the telescope. So basically in science, we only use reflective telescope because it's easier to build a larger mirror than there is manufacturing large lenses that redirects light in the exact spot that you want to. Okay, let's see how a radio telescope looks. So this is a radio telescope. From these lines are showing you the path of the light. So basically the light coming from the sky is reflected by the primary mirror. There is this big parabola here, is reflected to a secondary mirror, and here the light is reflected again on a room where we locate all the instruments to actually take data of the sky. The data here then are sent through cables to the control room, that is this building here, where as an observer are during observation or during the data analysis phase. These instruments are very big. In fact, this is the Sardinia Radio Telescope in Italy, where I work on. And this is the primary mirror has a diameter of 64 meters. And for scale, this is the size of a car when putting it near the radio telescope. So this is a massive structure. This is not likely the only radio telescope that we have in the world. We have a lot of them. I will only name you other 3 radio telescopes. The first is the Greenman telescope in West Virginia that has a primary mirror with a diameter of 100 meters. The Effensberg Radio Telescope in Germany that also has a diameter of 100 meters. And IRAM, that is in the Sierra Nevada mountains in Spain, that has a diameter of 30 meters. So, why do we need this big antenna to observe the microwave and the radio wave? Basically, we have to put together the resolving power, so the angular resolution, and the type of radiation that we want to observe. This radiation has a very big wavelength, and so to have a decent or good angular resolution, we have to build a very big mirrors and so very big telescopes. But let's see how actually we detect and so how we collect the data, the light that comes from the sky. And this is basically going a little more deeper in my work because I work on millimeter cameras, and this is me. So a millimeter camera is basically a cryostat. There is a fridge with superpower because can cool down things up to minus 273 degrees Celsius. And then we have to have an array of detectors. That is basically the camera with which we take picture of the sky. But why do we need a detector inside a cryostat? Basically, we want to reduce the noise that this detector see as much as possible. Because we want to detect very weak signal in the sky, and so we don't want to be dominated by noise of the environment. To make you understand a little better what I mean is, imagine being in a room with a lot of light, and you have to detect, you have to locate a luminous source. In this case, it's very difficult to see where the source is. You can see it, but it's very difficult. But if you turn off the light, you can really see better where the source is. And so basically, we want to reduce the environmental noise to actually observe better the sky. So just resuming a little bit, to observe the millimeter sky, we need a series of instruments that is basically the same of here. We need a telescope, a reflective telescope, with coupled with a millimeter camera that in the optical can be your phone, your eye, or a camera. And to speak a little more about what I do, basically, I do a little of everything because, as they said in my introduction, I work on instrumentation, and in particular, I'm responsible of the housekeeping of the cryostat. So basically, the group of devices that make the cryostat actually cool down to the temperature that we want. I developed some software to manage remotely the cryostat itself. So if I want to, I can turn on Mistral, that is this cryostat here, also from here, and it is located in Italy. Then I also participated in a lot of our observation where we saw a lot of cool things. And then I also I'm also part of data analysis, so trying to understand what we are actually seeing in the sky, try to determine physical properties, physical characteristics of the sources that we observe, and stuff like this. So let's see what we can actually observe in the millimeter sky. So the first thing that I want to talk about is the cosmic microwave background that I will call CMB from now on. So if we look at the sky with an optical telescope or with your eye, the background between stars and galaxy is dark, so it's black. But if we observe the sky with a sensible enough radio telescope, we see a little glow, a very faint glow that is uniform in every direction of the sky. So basically, if you see there or there or there, the intensity of this glow that you observe is the same everywhere. This glow is the strongest system in the microwave region of the spectrum. And basically, the CMB is the strongest evidence of the Big Bang theory of the evolution of the origin of the universe. Here, I show you a picture that basically tells us the history of our universe. So at first, there is the Big Bang. Then the universe, there is the inflation, so a rapid expansion of the universe, where the matter of the universe is basically a hot fog of particles and photons that are bound together and that are constantly interacting with each other. Light is bound to particles, so particles absorb always the photons in the universe, until with the inflation we reach a point where particles are cool enough that they start bonding together, forming the first atoms, and the light is free to travel through space. So it's not absorbed anymore by the particles themselves. This is the cosmic microwave background, and Then we had the formation of the first large-scale structure, formation of galaxy, and now we are here. So the cosmic microwave background, we can say that is basically a baby picture of our universe, because it tells us how the universe was when it was only 380,000 years old. You can tell me, okay, this doesn't seem very young, but you have to consider that the universe now is almost 14 billion years old. So this is very, very young. Okay, I told you before that the CMB is uniform in every direction in the sky. And it tells us also information about the temperature itself of the sky. And when we are observing it with a radio telescope, we basically observe something like this. And this is the sky at a temperature of minus 270 degrees Celsius. But if we observe with instruments that are sensible enough to see the little fluctuation of temperature that the CMB has, we see something like this, where the fluctuation of temperature here are of the order of 0.000001 degrees Celsius. So they are very small. This may seem insignificant because these fluctuations are very small, but they actually tells us this fluctuation as what enable large-scale structure to form. So galaxy or us or the life that we know. Also, observing the cosmic microwave background is very important because it tells a lot of information about the universe, as its age, its curvature, the composition of the universe, because from analyzing the distribution of in the sky of this fluctuation of temperature, we can determine the fraction of normal matter that we call baryonic matter, so us, the fraction of dark matter and the fraction of dark energy that compose our universe. We can also extract crucial information on inflation and on the density fluctuation that form now the large-scale structure of the universe, but also it can tell us information about the primordial gravitational waves. That, as for now, is the proof that we scientists understand how the universe works. We are still searching for this primordial gravitational wave, but we are building some very sensible instruments to try to detect them and prove our cosmological model. So this is the CMB, but this is not only useful at looking at like this, but if we zoom a lot, we can also see the shadow that galaxy clusters leaves on the CMB itself. And from this, we can study also the cosmic web. The cosmic web is basically a cosmic structure that is like this, and this is showing you the distribution of dark matter in the sky. Basically, we have knots that are where we have a well of dark matter, where actually we can find galaxy clusters. And these galaxy clusters are then connected by filaments of gas. Okay, so this is how a galaxy cluster look in the visible. And this is how a galaxy cluster look in the microwave. I will tell you now why it's important to observe the cosmic web. Basically, we have a discrepancy in our in cosmology. we, from our cosmological model, we know that in the universe it should be a certain amount of matter. But when we observe and count the actual matter that we see in the sky, we actually find only half of the matter. So it's very important to try to detect these filaments because we want to count. Simulation tells us that the half of the matter that we are missing is probably arranged in this filamentary structure that connects the galaxy cluster. It's very difficult to observe this structure because they are very, very faint. The signal is very, very faint. And only in the last years we were able to observe the first filaments. This is the first tentative detection of a cosmic filament where we studied the Able 399 and Able 401 galaxy cluster pair. And now we are expanding the analysis to other pairs to try to count as much as possible together. Okay. This is not the only thing that we can observe in the sky. In fact, we can also see galaxies, we can see nebulas in the Milky Way, and so we can do a lot of galactic and extragalactic science. Now I want to reinforce the concept that is very important to observe sources with as much as possible, in as much as possible wavelength, because every different type of radiation tells us different information about a source themselves. So maybe the next one will be the most explicative example to make you understand why I say this. So this is Hercules A, an elliptical galaxy that in the visible look like this. So it seems very normal, but when we observe it in the radio waves, these jets of plasma appears, and these are jets long 1 million of light years. So they are very, very long. So basically, we can see that there's a lot going on in this galaxy, and in particular, from this jet, we know that we are observing the synchrotron emission of the gas. This basically means that the synchrotron radiation is the radiation that is emitted by a relativistic charged particle when it's accelerated inside a magnetic field. So this radiation tells us information about the magnetic field of the system and the temperature of the gas and all the dynamical and physical properties of this source. Now I will show you the last three sources that we observed with Mistral, so with the red cryostat in which I work on. The first one is the Orion Nebula. Here you can see a superposition of an image that we took with Mistral and an image in the visible. In the visible, basically, we can see a lot of different colors and a lot of different things. In the Orion Nebula are located a lot different, very energetic and very bright stars that emit a lot of radiation that ionize the gas of the nebula itself. So basically here we are seeing the light emitted by the ionized gas that compose the nebula. And the different colors tells you the different type of gas that we are observing. For example, we have oxygen, we have oxygen, hydrogen, and we can see the and dust, and so we can see the red, the green, and also the shadow that is left by the dust itself. In the visible, we can't observe dust. Dust only absorb light, but if we try to observe this nebula in the microwave, we see this. And here we are seeing the emission, the thermal emission of the dust itself. So we can better understand the distribution of the dust inside the nebula itself. That is not possible to do in the visible, because in the visible we can see the dust. Another example is that of the Crab Nebula. That is a very young supernova. So basically is a star that died and exploded, expelling all the material of the star itself. This supernova is very young. In fact, here we can see a lot of things. The first thing that we see is the filaments that are composed by ionized gas and by dust. But we can also see a faint light blue glow here that is basically the synchrotron emission. The synchrotron emission is basically, we can't observe it in the visible because usually has very lower energies. But this supernova is so bright and so young and so energetic that the emission of the synchrotron is, we can see it up to the visible. But here we can see only a faint glow. If we observe in the microwave, we can see also the synchrotron emission, but actually we can see the structure, filaments, and the distribution of the gas inside the nebula itself. And this is not possible to observe, and we can observe this in the visible, only in the visible. The last example, the source that I will show you is Cassiopeia A. There is also a supernova, but this is a older supernova. So we can see here the synchrotron emission, but we can see only the emission by the gas and the shadow left from the dust. While if we observe it in the microwave, we see the synchrotron, but also the thermal emission of the dust itself. So I hope that I convinced you that it's very important to observe sources in different wavelengths. And thank you.
Thank you very much for your talk. Does anyone have any questions? Yeah.
Do you know what like energy is? Is it constant increasing or decreasing?
Is dark energy increasing or decreasing?
In the universe? In the universe? No, it's the same amount. We can create matter. So it's the same amount from the beginning of the universe. So it's not increasing, not decreasing.
Anyone else have any questions? Yeah.
Quick question: is it true that in areas where there are radio telescopes being operated, is it true that there are like limitations on the use of devices that actually emit radio frequencies,
Yeah.
things like Wi-Fi or radio? Is it true?
Yes, it's very true. In fact, when we go observing at the Sardinia Radio Telescope, there's no cell phone. We can use cell phone. We can use microwave to eat food. We don't have Wi-Fi, and we only can connect to internet via cable, because everything interferes with observation of radio waves. No?
So no cell phones, but both. So like no cell phones, but like things like camera or
Yeah,
even like
Internet line, yeah.
internet. But
Yeah.
microwave, so. But like a microwave, that the one you make foods, you just plug it to microwave, make food.
Yeah, no, we only use Ethernet cables to connect on internet, and we just use that, yeah.
Question up there.
Yeah, you were talking about the cosmic microwave background radiation. You said that small fluctuation, these small fluctuations lead to galaxies, the large scale structure of the universe. What causes those fluctuations?
We are still trying to understand it. Yeah, sorry.
One question up there.
You said you can remove the connecting the equation telescope that is made now, for example.
I can?
Uh,
Yeah,
Yeah.
control the, no, I can do it right now, because I need a special connection on my computer, and I don't have it here. But in principle, if I had this connection, I can do it here. We can do it in Rome, and the telescope is located in Sardinia, so on an island, and there is a sea in between us, so yeah. But I need this special connection, sorry.
Hi, you said you got to work on instrumentation and observation of other parts. What is your favorite part of the job?
No, I can't choose. No, I can't choose. I love everything. Yeah, I really like seeing the birth of the instrument and then using it and then actually analyze the data that I took with it. So I can choose. Sorry. No.
Bring the microphone on.
That's the best way to fight shyness.
Why radio wave folks have to be so?
Yeah, because we are observing very big waves with a big wavelength, and the angular resolution, so the size of the details that we can see on the sky basically depends on the structure of the telescopes and depends on also on the radiation that we are observing. So if we want to observe a radiation with a big wavelength, we have to build telescopes with a big mirror that can resolve every single wave. Yeah. No, I can't hear. Sorry.
So why is the max diameter of the telescope is 100 meters? Like, is there any point to make bigger or?
I think we can go bigger, but they never build bigger than this. But I think it's very difficult in the engineeristic side. So the structure.
Would it be useful?
Yeah.
Really?
Yes. I would love it.
In theory, what's the max diameter of a telescope? Which?
Of the universe. Yeah.
We're pushing back here.
Gonna walk around.
Perfect. Where did you study it?
What? The
Where did you study it?
I study in Rome, so in Italy. Yeah.
Is there anything that surprises you and challenges your understanding as study for of the subject?
Yeah, there's always a question following our research. So I think in science you never actually and knowing everything. So every research that you do opens leaves open question that you have to answer and find them. So I think it's like science is
Well, I saw an interview with Stephen Hawking, and he was asked by somebody, what was before the Big Bang? And his response was, that is an irrelevant question. And I wondered, is that the general opinion of
scientists.
do you agree with that?
I think that maybe first we want to observe, we want to understand what is in between the Big Bang and what we can actually study now, because there's a lot of things that we don't understand of the universe. So maybe we can do this little stuff, and then wondering what is beyond the Big Bang.
There's a question here.
Said, Maxwell diagram,
Yes, we can do it, and we have a lot of radio telescopes, but they are not called radio telescopes, they are called interferometer, because we put different antennas together, the different antennas look at the sky, and they have very, very high angular resolution. So we can do it, but we also lose a lot of information, a lot of signal in the sky, because they can see only the really tiny details and not the bigger picture. So it's good to have everything. So the very small, the medium, and the large.
There's a question here.
I had a question regarding the synchrotron emission.
Yeah.
So are there particular chemical composition of the synchrotron, like maybe a different pattern depending on like different like particles that make up like the synchrotron emission? Like what is the general composition of like emission, the particles that make that?
So the synchrotron emission is basically light. So it's not a composition, it's photons. It's light.
Okay.
Yeah. But it's this light is emitted by electrons or charged particles, so protons or ionized atoms that are in the gas and that are accelerated by a magnetic field. So the important thing is that it's a charged particle.
Yeah. So the composition of the gas that causes the charged particles that.
Yeah, it can depend.
Yeah.
Yeah, it's not the same everywhere. We can have everything is different in the region, so yeah. There's not a recipe, a precise recipe to have a synchrotron emission. The most important part is that we have a charged particle in a magnetic field.
So I think we have time for one, maybe two questions more. Your hand is up for a while. Well,
If I could ask is there any possible other universes exist? If so, what would they be like? Other fairies in another universe?
And the universe would like to this place. Oh, I don't know. I don't know. I would love to know. This is more a philosophic question and not a scientific one, maybe. We only know this universe here.
yeah, so maybe one more question. Yeah.
This is a great difference. Can you explain what causes the thread between the yellow dots?
The thread, the filaments?
Yeah.
Yeah, basically, this is the distribution of dark matter in the universe. And basically, it's just how the fluctuation of temperature evolved in time. And so now we should see something like this in the universe. And the filaments are just gas, while the knots are galaxy clusters. And so every galaxy cluster is connected by these filaments of gas within the atom.
Will the yellow dots develop into the planet or sun?
Inside the knots, yes, but inside the knots. The knots are only galaxy clusters. So it's a group of galaxies. Inside the galaxy, there's a solar system, the stars, and inside the solar system there are the planets. So it's lesser. It's not a planet or group of galaxies, solar system, and planets. This is the distribution of dark matter in the universe. It's from simulation. We do simulation with computers, just studying what?
Like the dark, like when you see it, there's like dark void.
No.
I think the question is, are the spaces where there are no light, is that the dark matter? Or
Oh, no. The dark matter is the luminous one. The dark matter is the luminous one. It's just, you have to think that where is dark matter, there is always matter. And so we are observing here the light emitted by the matter that is inside the dark matter. So everything is in one thing inside the other, yeah.
thank
As
you
the
for
galaxy.
all the great questions. For the sake of time, we're gonna stop the questions now, but you might be able to come up to Eleonora after and ask
What the question?
additional questions.
Yeah.